Okay, good morning, ladies and gentlemen. Thank you very much, Gina. So I'll start with a slide that Len Halsey asked me about yesterday. So he liked, where's Len? Len, okay. So this is nothing to do with the presentation. This is what happens when you don't plan for a lift pit. You end up with a set of stairs. They look nice, actually. They've got some carpet on them, but obviously without them. Someone didn't plan for a pit, so, or maybe they couldn't. So Len likes, you like that, Len, don't you?
No, I think that's every architect's instruction.
Anyway, more serious stuff. So Monte Carlo simulation to evaluate. Now, really, this is presentation not specifically about this topic. It's trying to introduce or to sell you the concept of Monte Carlo simulation. So Monte Carlo simulation is an advanced tool where sort of 2018, I think we're starting, things are becoming more complicated. Lift systems are becoming more complicated. I think we need more complicated or more advanced tools for solving and finding the round trip time. I've worked on this with Richard, who's here. Tools, we'll talk about tools. The clever researcher or the clever technician or the clever engineer knows to use the right tools at the right time. There may be tools that he or she will only use once in a lifetime, some which he will use once every year, and some which he will use every day. And the trick is to know when to use which tool. MP hard problems, interesting concept. This is a new concept, so the concept of an epoch. We've always talked about round trip time. I'm going to talk about a concept of an epoch. And I'll finish with an epilogue and some closing points. So what are the tools at our disposal? From a researcher's point of view, we have things like Monte Carlo simulation, but it's only one of many tools. I always tell my students, it doesn't really matter if you know it in detail, as long as you know what it does, what are the advantages, what are the disadvantages. One day you will think, I need that tool, or I need this tool. And as long as you have that vague idea about it, you can use it as and when you need it. That's a very, very successful strategy. Neural networks, dynamic programming. Mirko talked about dynamic programming yesterday. Reinforcement learning is very interesting because that's where you get things like the Go game. You remember the Go game where the human champion was beaten by a computer? Because what it could do, it was taught the rules. It could run, see the final outcome like chess, and teach itself. So it managed to do unsupervised learning, reinforcement learning, very powerful tool. Principal component analysis, and it's very much like this. You use the plane for certain things. You have chisels and different types of chisels and so on. So really knowing your tools, knowing what tool and what it does, rather than knowing it in detail, is very important. So what's Monte Carlo simulation? It's a method that relies on repeated sampling. We are drawing random samples from a population. The inputs are random. And it's especially powerful when there are multiple inputs and the degrees of freedom, they're coupled. One of them depends on the other. It's really a calculation tool. So the origins. Von Neumann was working. We had someone from Los Alamos, Brian Laubscher, who did. Brian is here, so you worked at Los Alamos. The origins of Monte Carlo simulation come from the Manhattan Project, when von Neumann, Stanislaw, and Ulam were working there. And that's where it was based on a famous casino where Ulam's uncle gambled away his money. That's why he called it Monte Carlo simulation. It's applied in investment, finance, very powerful tool in finance, computational biology, games that have outperformed previous algorithms, optimization tool, numerical integration, engineering, robotic manipulator arms, and even calculating the value of pi. This is a nice animated slide. So I showed it in 2012. I think it was the first symposium. So in order to calculate the value of pi, you have a very, very simple method. You get a large number of grains of rice. You draw a rectangle which has a 1 meter side. And someone starts throwing these grains randomly. Obviously, it has to be random. And we then get a rope. We fix the end of the rope here using a wedge. And then we draw a quarter of a circle. If you count the number of grains of rice when you've finished and divide them, that are inside the arc, and divide them by the total number, multiply by 4, that's the value of pi. Very simple tool. We didn't need to know anything about the area of the circle or otherwise. It just shows you the simplicity of Monte Carlo simulation. Where it becomes successful, you can repeat it 100 times, 1,000 times, or 10,000 times. A pair of dice is another example. What's the possibility of getting 5 on a die or one die?
1/6.
1/6. Yeah, okay, it's a simple question. Because I'm just showing you the simple cases, and as we moved, what's the probability of getting a pair of 1s? 1/36. Okay, 1/6 times 1/6. Because we know these things, it's simple. The equation is so simple. There are 36 possible outcomes. We divided one of them, which is 1 and 1/36. What's the probability of getting a 6 and a 1? 1/6 or 6/1. So it's 2/36. So that's 1/18. Okay, you see, I'm just trying to show you the progression of the complexity. What's the probability of getting 7 or more? A 5. You trust this guy? Okay, speak up. 57? I don't know if it's the right number. It's 6-1, 6-1, 1-6, 4-3, 3-4, 5-2, 2-5, and I think that's it. 6/36 is 1-6. No, it's not the right answer. We'll have another one this evening. We'll have a 5. We'll keep the 5 for this evening. You keep it. Yeah, that's gone. The 5 has gone. Okay. But why is so if it's easy, if it's that easy, why don't we do it in our minds? Because it becomes so complicated. So we have the reason it worked for the dice was small number of input random variables. We only have 36 possibilities. Equal PDF, so all of them are equal unless someone has played with the dice, and the inputs are decoupled. In our case, the inputs are independent. So let's take an example from passengers. This is the traveling salesman problem. Who has to deal with these sorts of problems? So you have to decide which city to visit first in order to optimize something. What's the number of possible combinations? We can start with one of 52 states. Then we go to one of the 51 remaining, 50, 49, and it's actually 52 factorial. So it's an enormous number. Let's look at an example of a building. We can travel to any one of 20 floors above ground. We have 8 passengers. So the first passenger can select any of 20 floors. The second one, the third, the fourth, the fifth, 6th, 7th, and 8th. We have 25 billion scenarios. No one can cope with that. A computer will take probably something like 5-6 hours to run. Days probably. I tried this once. I said to myself, it can't be, it must be fast. And it took hours and hours and hours before it finished. So what's the solution? If we can't do the whole population, what's the answer? We draw a sample. And that's what Statistics Office, the Office of National Statistics, they draw a sample. But what should the sample be? We can't draw any sample. It has to be representative. And this is Monte Carlo simulation. So you draw a sample out of the whole population. That sample, if it was drawn properly, it is very representative. So how do we draw a random variable? We have a probability density function. This is saying that that's the probability of a 1, probability of a 2. We integrate that, and then we can draw a random variable. We generate a random number from 0 to 1, drop this here, and then we get a number. That is called random sampling. And basically, very simplistically, some mathematician will be turning in their graves if they hear me say this, but this is basically Monte Carlo simulation. You know that there's a big population. You can't deal with the big population. You draw a random sample. What does a trial comprise? Well, originally, a trial comprised one round trip. But if we have destination, we have L round trips. I've chosen to call this an epoch. So an epoch is a new concept. It's actually L round trips. We do the first, second, third, fourth. That becomes an epoch. It's borrowed from, anyone know where it's borrowed from? The term? Neural networks. So let's have a look and as an example. So this is actually a nice template. People do templates to draw things on. This is a nice template. This is like a clean sheet of paper. And we say, how many passengers do we have in an epoch? And we split them on the left-hand side. We have the up-traveling passengers. And I've chosen to show the landing call as a triangle and the car call as a circle. So we've taken all of the up passengers, move them to the left-hand side, all of the down passengers to the right-hand side. That's nothing to do with the multi, this arrow. It's just, I'm just trying to split up on one side and down on the other side. And what we do then, we decide to group them. So we group them either by origins, for example. So we take all of the passengers that start in these origins, their destinations here. So we put them in the first lift. Some of them have to wait. Those in the second and those in the third. We could have grouped by destinations. Obviously, if we have up peak, it's better to group them by destination. If we have down peak, it's better to group them by origins. And that's a very simple explanation of this paper. If you understood this, anyone understood this? Raise your hands. Okay, more. Okay. If you've understood this, I'm a happy man, so I'll go away today a happy man. What are the potential applications? So there are loads of potential applications in lifts. The round trip time, that's where we started. General traffic. This is what Richard likes this paper because he calls it a dispatcher-free round trip time under destination. So we don't actually need to go into detail into how the dispatcher works. Twin is a nice example. Double deckers. And we can evaluate. So this is an example for twin. What you would notice here is that kinematics has become a very, very important component. It wasn't before. For the first time, kinematics and how things move, this is actually displacement against time. So that's the upper twin. That's the lower twin. And what we've had to do to avoid a collision, we've had to delay this lift so that when it comes down, it doesn't actually interfere with this lift. We keep the safe distance in there. So this is a nice example. Another example is multiple lifts in the same shaft. So if we have a rectangle, and we have, that's the first one goes up, we have to delay the second one such that it doesn't hit it, the third one, fourth. That's an epoch. See, that's a round trip. But that is an epoch. We've finished all, and it's not L times RTT. So let's conclude, and then we'll have an epilogue. I've got 4 minutes. So we rely on the principle of repeated sampling. You have to choose the size of the sample. So you decide it's 1,000, 10,000, 100,000. We talked about the different tools, like the carpenter. Other tools like Markov chains, Monte Carlo, MC, Monte Carlo Markov chain. Simulated annealing. Simulated annealing simulates how steel cools down. It's a very, very similar concept. Spectral analysis is people who analyze the frequencies. Sometimes, I'm sure Stefan does a lot of that. And we can see there are modern applications like twin, lift, and now the fun bit of this presentation. Let's philosophize. So if we look at the original equation, Gina and Dos Santos, that's 1972. I'm just trying to look at the contrast. And we mentioned yesterday, I still feel that H&S is actually a very intuitive way of understanding what happens. So that many assumptions here, many simplifications. Equal floor heights. Rated speed attained in one floor journey. Incoming traffic. Conventional group control. So that is really the beginnings, really, if you want to look at that. That was equation 7, which Gina showed yesterday. And now we're starting to look at kinemat. As the systems became more complicated, general traffic, incoming, outgoing, multiple lifts in the same shaft. So you can think of those two as a continuation of a journey. That's the first point of the epilogue. The second point, the original seed of this started with 2 students. I was teaching a course in 2008, 2009. We were looking at S, the formula for S, which is 1 minus 1 over n raised to the power p and so on. And 2 students said to me, 2 bright students, they make all my job really worthwhile. They said, why don't we actually take this and animate it? So they went away and they moved the lifts up and down and found the value of S. I said to them, well, this is actually Monte Carlo simulation. So that's the first one, Leith. I think he's doing a PhD up in Newcastle or Edinburgh. And that's the other student. So that's a nice idea how an original seed starts and you get something published from that. The third piece of the epilogue. Sometimes a new idea needs exponents and supporters. I think it's all good and nice to have an idea, but unless you have people believing in it. So these are the 2, I think, believers here. Stefan here? Well, Stefan is speaking later, isn't he? Yeah. Okay, so seriously, this is, unless you start getting people believing in something and then implement or thinking that it's worth implementation, that's when the idea becomes. And thank you very much. That's an application of Monte Carlo simulation, which I don't really understand, but it just looked very nice. See those colors? Colors are very nice there. Okay? I don't know what computational physics is. Thank you very much for your attention.